Everyone, I Chandan Kumar Bharti welcomes you. We are now all set for an exciting and stimulating day today. We will now be starting with the first technical session of the day. Our expert for this session of Gyan course is Professor Nilanjan Chakraborty. He is currently a professor of fluid dynamics at the School of Mechanical and Systems Engineering of Newcastle University. Previously, he was a senior lecturer at the School of Engineering of the University of Liverpool. He moved to his current position in 2011, where he heads the Fluid Dynamics and Thermal System Research Group. He graduated in Mechanical Engineering in 1999 from Jadavpur University, Kolkata. In the same year, he obtained an All India first rank in the Graduate Aptitude Test in Engineering examination. In 2005, he along with his co-authors was awarded the prestigious Gaddon Prize by the British section of Combustion Institute for the most significant UK contribution to the 30th International Combustion Symposium 2004. In September 2007, he was awarded the prestigious Hinselwood Prize for 2006 by the British section of Combustion Institute for his meritorious contribution to the combustion science. Professor Chakraborty is one of the recipients of the prestigious Hind Ratna Award 2015, which is one of the highest Indian awards given to people of Indian origin for outstanding contribution in their field of work by the Non-Resident Indian Welfare Society of India, an organization under the umbrella of Indian government. To date, he has published 159 papers in peer-reviewed journals and 112 conference publications. His research interests include direct numerical simulation of turbulent combustion, turbulence and combustion remodeling, Reynolds average Navier stroke and large eddy simulation, turbulent convection, natural convection of non-Newtonian fluids, melting or solidification related heat transfer problems in classical manufacturing and laser-aided manufacturing application. National Institute of Technology, Durgapur warmly welcomes Professor Nilanjan Chakraborty, sir, to initiate his presentation on the topic of computational modeling of turbulent flow and scalar transport. Sir, thank you.
Thank you for the kind introduction. So I will start with the first lecture. So in the first lecture, I'll talk about the governing equations and their significance. If we are interested in computational modeling, we will need to actually know the governing equations because these are the building blocks, and based on that we can actually develop the concepts. If you don't understand anything, please stop me there. Okay? Roughly, the sessions are going to be 1 hour long, but it is not strictly 1 hour long because I will take as much time as I need to actually explain the concepts. So please bear with me. Okay? So very often, whenever I see students looking at CFD simulations, I see this approach. They try to actually directly jump to CFD softwares without taking into account that CFD, computational fluid dynamics, is an interaction between mathematics, fluid mechanics, and the fundamentals of CFD, which is the numerical techniques. In addition to that, you have to consider the physics of fluid motion, and that's the part which I'm going to focus about in next 5 days. Obviously, as the name suggests, I'm going to focus on the turbulence modeling. But if you look at the books of turbulent flows, they mostly talk about how to actually deal with momentum transfer. They don't actually talk a lot about scalar transfer or scalar transport. And that's where the innovativeness of this course lies. Because you will see many of the things which I'm going to talk about in the next 5 days are not necessarily mentioned in standard textbooks. So, effectively, this is the philosophy I believe in, and I believe more or less all the leading computational fluid dynamics research groups essentially believe in this kind of philosophy. Effectively, the mathematical modeling feeds into high fidelity simulation. High fidelity simulations effectively gives you huge amount of data. Intelligent data mining can lead to model development for engineering applications. And eventually, they translate into engineering design of new devices. So, firstly, CFD is not necessarily equal to simulations by commercial software, so it's not equal to Fluent, if you're familiar with Fluent. Please understand that when the cutting-edge CFD research is talked about, very often people actually use in-house code, open source codes, and they are run on massively parallel simulations on the world's first, some of the fastest supercomputers. This one used to be world's second one, is heavily used for CFD simulations. Frontier is number one at the moment, based in the US. The users of Frontier are some of the top CFD researchers in the world. But in order to actually utilize these machines and properly, you need to know the underlying physics of fluid flow. So essentially, that's my overarching aim for this course. So why computational modeling of turbulent flows? As you heard, it is ubiquitous in nature. Most industrially relevant flows are turbulent. And you can see this is just a jet flow visualization. You can see the turbulent, non-turbulent interface here. If you look at the Panama Bay on the top, you can see the same flow structures in this region. And the same kind of thing qualitatively can be seen at gas turbine combustor. And in astrofluids, if you think in terms of Jupiter's red spot, it is nothing but a large scale eddy. So effectively the physics that we are talking about, you can imagine it is actually valid over a large range of length scales. Navier-Stokes equations are the most difficult equations known to mankind. The nonlinearity Navier-Stokes equation makes the analysis of turbulence a very difficult task. There's a $1 million prize if somebody can actually come up with an analytical solution of Navier-Stokes equations for all kinds of flows. Some mathematicians are still trying. We engineers don't care, we bypass the problems by solving the same equations by computational means. And effectively that's what we talk about. But you can actually appreciate how difficult it is. Heisenberg once mentioned, when I meet God, I'm going to ask two questions. Why relativity and why turbulence? And he believed that God will answer the first. So you can appreciate why we are talking about turbulence as one of the difficult problems in physical sciences. You can see from Leonardo's sketch that turbulent flow actually shows a large range of length scales and time scales. How large that range is, we'll see later today. So all these difficulties are exacerbated by the presence of chemical reaction in turbulent reacting flows, because chemical reaction is a nonlinear function of temperature and species mass fractions. In addition to that, if you have heat release changes density. That density effectively affects everything happening within the flow. So it is a closely coupled system. It will happen even in natural convection, but in the turbulent reacting flow, the interaction between the energy equation and the rest of the other governing equation is much stronger. So these are the main objectives. I am not going to dwell on this very long. So you will have these notes, I believe, at some point, so you will know these things. I think this bit is important. everybody actually looks at turbulent flow differently because it's a difficult issue. Everybody approaches it from different point of view. I've been very lucky to actually interact with some of the people who actually wrote these books. And very often, some of them were really annoyed if I was actually looking at somebody else's book. So there are strong feelings between people. Okay? So personal preference matters in turbulent flow research, but we are talking about science here. Okay? So I have tried to filter out my personal opinion on the subject. I'll present you with the facts, but all of them are good books, even though some authors don't like the other authors' books, but there are advantages and limitations in all of them. Okay? Not expecting you to read all of them, but if you can, great. Just before I go, obviously what I am going to present, it's an outcome of research which I did over 20 years. And here are the collaborators, my PhD students, postdoctoral research associates, and the grants that I got, which enabled me to do the research. And essentially what you are seeing, the filtered version of the outcome, which now can go into some kind of a monograph kind of thing. So starting point, so governing equations, numerical simulations, model development for engineering calculations, and that's what the logic is. And that's basically the logic which I follow in my research. So now we'll start talking about the equations. As the slide suggests, whether it's trending or not, you still have to learn it. So probably this is going to be nothing new for most of you, but I think it is important to actually recapitulate. We'll talk about mass conservation equation, momentum conservation equation. Altogether, all of these things are referred to as Navier-Stokes equations. I'll use tensor notation heavily later on, so I'll expect you to know about the tensor notation. Navier-Stokes equations are nothing but Newton's second law of motion written for fluids. Effectively, in Newton's second law of motion, we write generally in terms of F equal to ma, F being the force, m being the mass, a is the acceleration. Here, effectively, what you are seeing, mass times acceleration divided by volume, that's why density appears. And that effectively means this side is force per unit volume on the fluid. Force comes because of the pressure as well as for the viscous action, and on top of that you can have body forces. So that's what is referred to. Here I will use tensor notation as I mentioned earlier, so in the tensor notation those equations can be referred in this manner. So let's talk about the derivation of these equations, because I, both as a student as well as a researcher, found the derivations extremely insightful. Because if somebody throws the equations, it's a very dry stuff. Because you don't have an appreciation from where the terms essentially come from. And that's why I want to actually address this. So most of us, when we were a little kid, played with little blocks, and with little blocks we made some arbitrary shape. So if we consider this is one of our little small blocks, and based on this is a block of fluid, and if we have several of that, we can make any flow configuration. So if our governing equation is valid for a small block, it should be valid for any arbitrary shape. So let's say x and y are the coordinates at the center of this block. Using Taylor series expansion, U is the velocity normal to this space, that's the x component of velocity. V is the velocity in the y direction. If U and V are the velocities at the center of the block, rho U minus this part is essentially the mass flux for this phase. It comes from the Taylor series expansion. And similarly, for this phase, it becomes rho U plus del x of rho U delta x over 2. Delta x over 2 because I'm taking from the center. Clear? And similarly, for y direction, the mass flux is rho v minus del y of rho v delta y over 2 because I'm taking with respect to the center. It becomes plus or tau. Okay? The total mass within the control volume is density times delta y times delta x. If we consider immediate normal to the board, then delta x times delta y times 1, which I did not show, is the volume times density gives us the mass. Now, rate of change in mass within the control volume. So this is the mass flux, so that's why the area for that is going to be delta y times 1. This one is coming in, that's why positive sign. This is going out, that's why again it's multiplied with delta y because this is the area we're talking about, but with a negative sign. Okay. For this one, now the area is delta x times 1, but it's coming in, that's why positive sign. This one is going out, that's why negative sign. Clear? And if you do the algebra, it will come up with this, and that gives rise to the rate of change of mass within my control volume. Now, I have already drawn my control volume. So my control volume shape is not changing with respect to time. The rate of change of mass within the control volume can only take place because of the rate of change of density within the control volume. So that's why it is given by del rho del t times delta x times delta y. Okay? And if we consider these two together, ultimately we'll end up with this equation, which is our well-known mass conservation equation for 2 dimensions. You can do the same thing in 3rd dimension and you will get the mass conservation equation. Any issues with that? Now, let's move to momentum conservation equation. This time, it will look a little bit different. So again, I'm starting from the center of this control volume. Let's consider the momentum. Momentum is a vector, so we are considering only for the x component, just for the demonstration purpose. So, rho times delta x times delta y times 1, which I have not shown, gives us the mass, right, for the control volume. Mass times velocity component u gives us the momentum in the x direction. As I told before, that I have drawn delta x and delta y before. Already, the control volume is predetermined. So, delta x, if I take the derivative of that, delta x times delta y will come out of the derivative. You will just have del t will walk only over rho. Rate of change of momentum. So let's see what happens then. Rho u square is the momentum brought by the flow in this direction. But why del x times delta x over 2? Because I'm doing Taylor series expansion with respect to the middle point. Similarly, this one gives you similar contribution, but this time with plus. Clear? But if I am considering 2-dimensional flow, it has 2 components as well. So in the y direction, this normal component of the velocity on top of this boundary gives you rho v square minus del del y del y. Once again, because I'm doing Taylor series expansion with respect to the same thing you get, but with a positive sign. Clear? But whatever flow is coming through this boundary, it also has an x momentum. And that's what I have shown with this green thing. Okay? So that will give you rho uv, that is the contribution at the middle point. But now I am doing Taylor series expansion, that's why minus del del y of that delta y. Clear? Same contribution comes from here, but this time with plus. Does it make sense? Here, similar thing can happen through these boundaries for y momentum as well. The flow that is coming through this boundary is also bringing some y momentum. Again, if rho uv is that component, then if we do Taylor series expansion, I'll get rho uv del del x of rho uv delta x over 2 because I'm doing Taylor series expansion with respect to the middle point. And you will see similar contribution, but this time with plus. Clear? Fine. Now, think about your bank account. Okay? This is the net effect in your bank account. These are whatever is coming in and whatever is going out. Income and your expenditure. So, effectively, this one is coming in. That's a positive sign. This one is going out. Negative sign. This one is coming in. Sign. Going out. Negative sign. Clear? On top of that, there can be contributions because of different forces. Now, force is again a vector. So, the components we will need to consider. So, I need to consider about the x component of the pressure is the force in the x direction as well. Fine? So, now, if we consider the v momentum exactly in the same manner, it is coming in, that's why you will have this to be positive, this one is going out, that's why negative. This one is coming in, that's why positive, this one is going out, that's why negative. And similarly, we need to consider the y component of the pressure force, viscous force, and this is the body force contribution. Okay? Body force means effectively per unit volume, something constant is work. Okay? Now, let us find out the pressure force. So if P is the pressure at the center of the control volume, this is the pressure on this space, this is the pressure on this space, this is the pressure on this space, this is the pressure on this space. Again, I'm doing Taylor series expansion. I'm considering delta x and delta y to be sufficiently small, so I'm actually ignoring the higher order terms. So I'm assuming that is understood at this stage. Pressure always acts inward direction. So effectively, it is acting in this direction for this space, in this direction for that space. So net force because of pressure in the x direction is this times this area, which is delta y times 1, minus, because I'm talking about positive x direction, it is acting in the negative x direction, this times this area with a negative sign. After a little bit of algebra, we will get this. The same concept, if you do that, this is working in the positive direction times the area, this is working in the negative y direction with the area, you will get this. Clear? You must have seen this several times in your solid mechanics. More circle and so forth. But effectively, we are talking about continuum mechanics. Whatever you actually learned in terms of the solid mechanics course, there as well in fluids. So tau xx is the normal stress coming because of the viscous action. I'm just doing Taylor series expansion, so it will be tau xs. Okay? Similarly, tau yy is the normal stress for the y direction. Here it is tau yy plus delta yy delta y. You have shear stresses as well. They are shown with the green arrows. So if tau xy is the shear stress in this direction, you know the complementary shear stresses. So effectively here it is going to be the other direction, tau yx plus delta yx delta x plus delta x. Tau yx is working in this direction. That means here the term is going to look like this. Here. Now, if we are interested in the x direction, this stress times this area minus this stress times this area. That's positive x direction. But in addition to that, that's because of the normal stress contributions. We have to consider the shear stress contributions as well. So this green component times this area, this green component times this area, but in negative y direction. So that's what I think. If you do a little bit of algebra, it gives you this. Similarly, for y direction, it is working in the positive y direction. So this times this area minus this times this area, because this is working in the negative y direction. This one is working in the positive y direction. So this times this area, which is delta y, and this times this area, but with a negative sign, because it's working in the negative y direction, gives you this. If I now put all of them together, this is what you get. And following the same procedure, you will get this expression for the y momentum conservation, and that gives you this equation. Obviously, there will be an extra term here and here if you are considering three-dimensional. But hopefully the idea is clear. Now, the way I have shown this equation or this equation, they are called conservative forms, because they are directly coming when I am considering conservation of momentum. I can actually simplify them further. If I consider any of those equations, for example, just because this equation is there on the slide, I can show that by chain rule, you can get this the whole thing. But we have already shown, because of the continuity or mass conservation equation, this is identically equal to 0. So I can actually drop this, okay, to 0. But at this point, a cautionary remark, you can only do that for single phase flows. Okay? If you have multi-phase flows, and if you are writing your mass conservation equation for gaseous phase, say if you have some droplets there evaporating, then you are generating something in terms of the gaseous phase. So this is not going to be equal to 0. You have to take that into consideration if you are writing the equation in non-conservative form. But if you are writing simple single phase, then this part goes to 0, and effectively this equation boils down to this equation. Okay? In other words, this part is nothing but our well-known material derivative or substantial derivative or total derivative, whatever name you want to call it. just for completeness sake, because I have found in 20 years' time, sometimes these things are not mentioned. Maybe that's not the case for you, but I'm not taking any chances. But what's the difference between here I have the time derivative, here I have a time derivative? What's the difference between these two? Effectively, often in physics, we actually look at a given point in our system, and we are essentially seeing what happens at that given point. It's equivalent to, I have a pipe, I'm putting a probe at a certain location. So I'm actually seeing different fluid elements passing through that point at different time instants. Clear? And that's what I'm measuring. That's called Eulerian frame of reference. So effectively, when I'm talking about this term, I'm looking at the change in velocity with respect to time in Eulerian frame of reference. For convenience sake, we generally use Eulerian frame of reference in fluid mechanics most of the time. There are applications where people use Lagrangian method as well. The other one, if you actually put your reference frame on the fluid and you are tracking a fluid particle, and that's what we actually do in solid mechanics, then you are going to see this change with respect to time. Why? If you consider you have a football match and you are actually focusing on a point in the football pitch, in Eulerian frame of reference, and your camera is focusing on that point all throughout the match, the ball may not pass through that point throughout the match. You are losing everything there. That's why in solid mechanics you actually track the ball, which is the most important part. Effectively, if you track the ball, essentially you are going to see that. When I talked about F equal to ma, Newton's second law of motion is written in terms of Lagrangian frame of reference, and that part effectively is ma divided by the volume, and that's why you get density. Mass divided by volume gives you density. Now, I'll go into energy equation. If you are going for scalar transport, you need energy equation most of the time, especially if it is a heat transfer problem. So this is specific volume at constant, as well as specific heat at constant volume. Tf is the reference temperature. I will consider the kinetic energy part. Okay. Obviously, if you are thinking in terms of 3D, there will be W square. The idea is exactly the same. Rho E is the energy flux for x direction. Rho VE is the energy flux in the y direction. I'm doing the Taylor series expansion with respect to the middle point. That's why negative del x that I compute. Ignoring the higher order terms, here it becomes plus, here it is negative, because I'm doing in terms of this direction, this distance, that's why minus del y over 2. Here the component is plus. Clear? I'm doing first law of thermodynamics once again. Think about your bank balance this time. There are ways to actually express first law of thermodynamics, but ultimately it is nothing but bookkeeping of energy. If you understand how your bank account works, you know how first law of thermodynamics works. Effectively, this one, heat transfer, is your income. That comes in your bank. You actually spend for your mechanical work. The flow is bringing some amount of energy, so this one gives rise to a positive contribution when you multiply that with the corresponding area. This is going out, that's why negative sign. Clear? This is coming in, So that's why this times this area positive. This is going out, that's why. So all incomings have positive sign, all outgoings have negative sign. That's what happens in your bank account, isn't it? And if the net contribution is positive, our control volume becomes richer in terms of energy. If your income is greater than your expenditure, your bank balance goes up, you become richer. In our context, the systems becomes richer in terms of energy, that will be reflected in terms of rising temperature. If your expenditure is greater than your income, your bank balance goes down, you become poorer. Similarly, our system will become poorer in terms of energy, that will be reflected in terms of decrease in temperature with respect to time. That's all it is. Clear? Let's find out heat transfer. So I have, let's say, this is volumetric heat generation that can be heat released into combustion or reacting fluids. Can be something else as well. Okay. If I consider this is my diffusive heat flux and Qx is the value at the middle of the domain, heat flux is a vector, that's why subscript x and y. So this is the value in the space. Again, I'm doing Taylor series expansion. Similarly, this is the value on this space. For the y component, this is the value for this space. I have explained several times, so I'm not repeating it again. And for this one, similar things, but with a positive sign. Clear? Net contribution, whatever is coming in. So if this is coming in, this times area, this is going out. So this times the area subtracted. This is coming in. So this times this area with a positive sign. This times this area negative sign. And then if we use Fourier's law of heat conduction for the heat flux components, end up with this. In your first law of problems and when you learned about work and heat, you must have done several piston problems, piston gas piston problems. If you remember that if the piston moved against the pressure, then it was a positive work. If piston moved in the direction of the pressure, then it's a negative work. So if work done against the pressure, that was a positive work. If work done in the direction of the pressure, it's negative work. We'll follow the same consideration. And you can actually see where you are expected to have negative work, where you are expected to have positive work. Based on this diagram, where the pressure is working and the velocity is working. Because we are talking about power here, we are not talking about work. That's why the velocities are coming in rather than displacements. Clear? So this one will give you negative work, this will give you positive work, this will give you negative work, this will give you positive work. And how you get the work? Essentially, this pressure times the area gives you the force, force times the velocity gives you the power. Clear? And if I do this, then I'll end up with this expression. Viscous forces and the velocities are shown here as well. Same convention as before. Okay. So if you actually put the same convention, again multiply the stresses with the corresponding area, after a little bit of algebra, you will end up with this. Now, if we put all of those things into our energy conservation equation, this is what we get. dx. That's the complete form of energy equation. The problem is in the literature, there are various ways of writing energy equation. Each one differs from another by a slight amount. Often confuses people. But effectively, all of them are talking about the same thing. Before I go any further, you can appreciate these terms are basically originating from fluid coming into the control volume, going out of the control volume. This is essentially telling the transport process by virtue of fluid motion, which is often referred to as advection process. Okay? These terms originated because of the thermal conduction or thermal diffusion. They are referred to as thermal diffusion term. These two terms, the pressure contributions, they are essentially the contribution for the flow needs to do in order to sustain the flow. It's the flow work part. Okay? And this is the viscous work part. Effectively, because of that action, mechanical energy converts into heat energy. So if I actually take these terms on the other side, we will get this, and that gives us specific stagnation enthalpy, where Cp is the specific heat at constant pressure. And then one can actually write this equation. But please note now, this time there is a sole del P del T term on the right hand side, which was not there in the equation when I wrote this in terms of the specific stagnation internal energy. Everything else looks more or less the same, but suddenly one extra term has originated. Talking about the same physics, writing the equation slightly differently. So please keep that in mind. If I write this equation for sensible enthalpy, at the moment it is written for the specific stagnation enthalpy as shown here. And if we use continuity once again, this is written in conservative form, you can get this equation. Okay? Because of chain rule, effectively this part will boil down to this. And if you write the same equation now by expanding the kinetic energy part, and for these parts effectively use the momentum conservation equation. So you replace this is the left hand side. You can compare, this is the right hand side corresponding to this. Take the left hand side, it's the corresponding right hand side. This boils down to this, and you get this expression. Again, same equation physically remains exactly the same thing, looks slightly different. Alternatively, you can actually write the same equation in this form. Now, you need to appreciate one important thing at this point. So far, whatever I have talked about is valid for all kinds of fluids. Newtonian, non-Newtonian, incompressible, compressible. Single phase is the only limitation. Otherwise, you'll have some extra terms. At this point, this is the first time I'm making an assumption.
So what exactly is the contribution by del P by del T here?
It depends on which application you are seeing. If you have a non-dimensional number called Eckart number, it's a very high Eckart number, you will have that contribution playing an important role. Okay. In the case of incompressible fluid, that contribution is often negligible. Essentially, you can drop quite a number of terms from this equation. You can, if you do an order of magnitude analysis, you will see this term, and this term often will drop out. Okay? But that is not necessarily the case when you are talking about compressible flow or high-speed flows. This term may play a very important role for very low Reynolds number flows. So, at this point, this is the first time I am making an assumption. If it is a Newtonian fluid, because you can appreciate on the left-hand side I have velocities, but these quantities here, when I'm talking about tau ij, shear stresses, I don't know at this point how I can actually express them in terms of the velocities, because they measure velocities. This is where the first time I bring in a simplification. Often people say Navier-Stokes equation is an approximate equation. They are coming from the physics background. If you're looking at this equation from the Boltzmann's equations point of view, Navier-Stokes equation is not an approximate equation. Navier-Stokes equation is an exact equation. At this point, it becomes an approximated equation. Okay? If I'm dealing with a non-Newtonian fluid, this relation will change. So the resultant equation from this point will differ depending upon the fluid that you have. Okay? The compressible flow, this contribution will go away, because thus divergence of velocity field we can show for incompressible fluid, divergence of velocity field goes to 0. Now, if you are dealing with reacting flow, like combustion, the volumetric heat generation is not constant. It changes from one place to another. How you can actually express that? Let's say I can actually express that with a fuel reaction rate times the heat of calorific value of the fuel in this manner. Why negative sign? Fuel is a reactant, it's consumed, so this quantity has a negative sign. So negative makes it positive. It releases heat. Okay? How do you get that? As indicated, this one is expressed in kg meter cube, and here effectively this one is in terms of kilomole per meter, and this is molecular weight. How Q is considered? In this manner, YF0 is the fuel mass fraction in the unburned gas. Cp, obviously you know, specific heat at constant pressure. P0 is the unburned gas temperature. T adiabatic is the adiabatic flame temperature. So if you have done chemical thermodynamics, you should be able to actually relate to those. So effectively, if you have a chemical reaction like this, effectively you can write this quantity as like this quantity as like this quantity like this, and your Q becomes this. If A is the flow. Okay? And this quantity, which is the volumetric heat generation, in that case is expressed in this one, which is nothing but summation of the heat of formation and the reaction. Clear? But if you have a mixing problem or a chemically reacting system, we have talked about mass conservation, momentum conservation, and energy conservation. That's not enough, because we need to consider the species conservation as well, because you are going to have different concentrations of different reactants or products at different locations. And that's why we have to consider species conservation. But species conservation is very similar to mass conservation that we discussed earlier. So species when we are talking about species conservation, think about this control volume. Once again, rho times delta x times delta y times unit depth gives you the total mass of my control volume. Y alpha is the mass fraction of species alpha. So the amount of alpha that is remaining within the control volume is given by rho y alpha delta x times delta y. The rate of change of that with respect to time is given by this. I have already explained delta x and delta y is constant because I have defined my control volume like that. Comes from where? What I talked about, Eulerian frame of reference. That's why I have considered my control volume as predetermined. I can change my shape of my control volume as a time-dependent thing that will bring extra terms into my consumption. Most of the time I don't need that, but that option is there. Rho uy is the mass flux because of the fluid motion in the x direction. Similarly, rho vy is the mass flux in the y direction. I'm doing Taylor series extension once again from the center of the control volume, and that's why I'm getting this contribution, this contribution, this contribution. I've discussed it enough, so hopefully you can follow that. Now, this is my mass transfer flux. Okay? Again, if I consider mx and my at the center of the control volume, these are the mass fluxes in the x direction, y direction, boundaries. And I have generation rate or destruction rate of alpha. Clear? How I define that mass flux? Using Fick's law. To be specific, Fick's first law of diffusion. But there are, again, at this point, I am making an assumption. There are more complex, more detailed way to actually express that. Okay? So, now, once again, that bank account analogy. Whatever is coming in, positive sign, whatever is going out, negative sign, whatever mass flux coming in, positive sign, whatever is going out, negative sign, plus whatever is generated. Unfortunately, that doesn't happen in your bank account. It would have been very good to have that, right? So once you do the simplification, you end up with this. And that brings us to this equation. Once again, I want to emphasize, after this, everything is okay. Everything is general. At this point, if I now replace mx and my with Fick's law, it becomes an approximate equation. Okay? But generally, we deal with this form most of the time, and that is this. Okay? Now, this part comes because of the affection process. This is your transient term. This is your molecular diffusion term. And this is either source or sink term. If alpha is a reactant, it is being consumed, this term is going to be negative. If alpha is a product, that means as a result of chemical reaction it is generated, this will be positive. Clear? So, one important thing to notice, if this D alpha mass diffusivity, there is no reason to assume that this diffusivity is going to be same as thermal diffusivity. And often one gets a very important non-dimensional number or Lewis number, which is defined as thermal diffusivity to mass diffusivity. And this can also be expressed in terms of Schmidt number to Prandtl number. Schmidt number is the ratio of kinematic viscosity to mass diffusivity, and Prandtl number is kinematic viscosity to thermal diffusivity. Why I actually indicated that is, I'm sure you heard about hydrogen as an alternative energy factor. If you are actually dealing with hydrogen, you have lots of species like H2, H. These are light species. Lewis number is extremely small. They diffuse much faster than the heat. And that process induces some extra complexities which are not there in conventional hydrocarbon fuels. And that effectively changes the whole behavior. Why this one, this term, is related to, you may remember, to the heat release term. So that means if the reaction rate changes, it changes. These are the stoichiometric coefficients, the balanced chemical reaction. Okay? So, please keep that in mind, that what I was telling, that this one changes the chemical reaction. Chemical reaction essentially changes the heat release rate term. If heat release rate is changing, that will affect temperature. Temperature through the state relation, like if I consider ideal gas law T equal to rho R T, will change density. Density will change, will induce change in velocities. So it becomes a completely coupled system. Okay? So, if you think about that, when you are talking about a turbulent reacting fluids, effectively, even for small Mach number, density change can be 8-fold in hydrocarbon combustion or hydrogen combustion. So you have to consider the change in density as well. So effectively, you need governing equations for U, V, W. These are your unknowns. You need pressure, you need density, you need temperature, you need species mass fractions. Okay? So how many of them? 3, 4, 5, 6 plus n number of species. Okay? But if I actually sum all the species mass fractions, I'll get unity. So I don't need n number of species equation, I just need n minus 1 number of species equations. So that means I have all n plus I unknowns for n species system, and effectively for gaseous phase combustion often we use P equal to rho RT. Just for completeness sake, these are 3 major modes of combustion. Premix combustion, where the fuel and oxidizer are homogeneously mixed prior to the combustion process. That's what happens in spark ignition engines. In the case of diesel engines, if your fuel and oxidizer are completely separated from each other, that's a non-premix combustion. Very often nowadays in engines, essentially you go towards the partial premix combustion. In direct injection engines, they are injected separately. They are allowed to mix somewhat before the combustion process is initiated. So effectively, at the end of the lecture, we should have basically nuts, bolts, tools, and hammers. We have got to actually handle the actual problem. With that, I'll stop. Happy to answer those. Anything?
Sir, in reactive flow, how this phase change is calculated? Because
So far, I'm talking about single phase fluids. You can have, if you consider pure premixed flames in gaseous phase or non-premixed flames in gaseous phase, whatever I have mentioned, that's sufficient. If you are talking about droplet combustion, there will be extra source terms coming in.
So what are the examples of like this chemical reacting flow where phase change is not occurring?
In SI engine, spark ignition engine, where you are actually what happens in your cylinder, at that time you have fully vaporized fuel and oxidizers are homogeneously mixed.
Already we are assuming that fuel are already atomized.
That happens in the pre-chamber or in older ages in carburetors. When you are actually dealing it within the system, it's already single phase. In gas turbine combustion, when the combustion actually takes place, it's often a single phase process.
Sometimes I have seen that there is some issue that in our society that how X momentum is reaching to Y surface, for example, how Y momentum is equal to the vertical surface. That you have shown here by your line. So sometimes I also get difficulties here. I didn't understand. So there are
The momentum, when we are thinking about the momentum, it is basically bringing the fluid in a given direction. But if the flow is going in that direction, it is actually carrying that momentum in this way. That's why I wanted to show in that manner. That's how I visualize it. Your velocity is in this direction, but flow is in that direction. So it's basically carrying the flow, your momentum in that direction.
some pictures I have heard that
Mass flow rate is not a factor, but mass flux is a factor. Mass flux is a factor. Yeah. Just like heat flux is a factor, mass flux is a factor as well. So where we actually wrote, this is for the x component, this is for the y component.
Actually